Welcome to my video on 5-2b graphing systems of inequalities. To start us off in our do now, I'd like for you to match each inequality with its corresponding graph. So to do that, let's quickly review how to graph inequalities on a coordinate plane, right? We know that they are not graphed much differently from their linear equation counterparts, right? We plug it into our calculator, we get our points. The main difference has to do with their inequality symbols. Whether it's a greater than symbol, a less than symbol, a greater than or equal to symbol, or a less than or equal to symbol. So things we need to remember. When we see a greater than symbol, this guy right here, it's going to be represented with a dashed line, and we will be shading above the line. Now, why is that? Well, remember, it's a strict inequality in that we only want things that are strictly greater than. So anything on that equal to line will not count as a solution, okay? The less than symbol will be represented very similarly with the dashed line, but this time we will be shading below. As for the or equal to's, the greater than or equal to's or the less than or equal to, right? They will follow the shading of their corresponding strict inequality, but this time they will be graphed using a solid line to represent that every point on the line is a solution to that inequality. We are accepting the or equal to's, right? So when we go to something that's matching, like the example we have in front of us, the first thing we should pay attention to are our inequality symbols. We have a less than symbol, a greater than or equal to symbol, a less than or equal to symbol, and a less than symbol. Okay, so let's start with the easy ones. We have two different inequality symbols right here. So if we have something that is greater than or equal to, we should have a solid line and shading above. So which one of these answer choices has a solid line? Well, that's 2 and 4. And which of those two are shaded above? That would be graph number 4. So we are going to match B with graph number 4, just based off of the symbol alone. Now, if we looked at the y-intercept, right, about 1/2, that's good. It's a negative slope. Looks like it matches. Let's look at the second easier one, right? This other unique symbol, the less than or equal to sign. We should be expecting for a less than or equal to sign a solid line and shading below. Well, we've already used the other solid line, so that only leaves option number 2. Is it shaded below? Absolutely. So number 2 is going to be paired with C. So now we look at the two inequalities that are both less than. If we are looking at a less than, we should have a dashed line and shaded below, which we should see here, right? These are all both dashed, and we are shading below the line for both of these. So for something like this, we're going to compare our y-intercepts first. This is a +1, and this is a -9/4. Well, this y-intercept right here is +1, which means that A is going to match with 1, and this one right here, right, is in the negative area, which would match with option D. Okay, so just by looking at our inequality symbols themselves, we are able to match the graphs quickly without plugging each one into our calculator. So now if anybody needs to write down these steps for reviewing graphing inequalities, this is what we should do. Make sure you graph the y equals mx plus b form of the inequality, right? We call this our boundary line. You can do that by plugging into your calculator and finding points. You could do that by going from your y-intercept and counting the slope, but you want to make sure you graph those points. If it is not in slope-intercept form, y equals mx plus b, you must solve for slope-intercept form, remembering if you multiply or divide by a negative, the inequality sign must flip. So that's something you need to remember. The next thing we do when we graph these inequalities is we have to remember, do we connect the points with a solid or dashed line? So basically, if there is no or equal to sign, and it's a strict inequality, that's what we call it, it would be a dashed line. So that's this or this. If it is an or equal to, we would represent it with a solid line. So that is these two. The last thing we do is we make sure we shade. Okay, and we're shading where the solutions can be found. Now, as we said in the do now, we shade above for anything that's greater than. So that's a greater than symbol or greater than or equal to symbol. We shade below for anything less than or less than or equal to. But please remember that these rules are only if the Y is on the left side of this symbol. Okay, if you have any doubt, remember that you can always use a test point. How do we use a test point? Well, we take any point on the graph and we plug it in. If it satisfies the inequality, we would shade on the same side as the test point. If it does not satisfy the inequality, we shade on the opposite side. Okay, so we are going to be using these skills today for our graphs. So now let's take a look at the graph that's already provided for us. We have that the red inequality is the inequality y is greater than or equal to negative 1/3 x plus 1. The blue inequality is less than, y is less than negative 4x, and then we have an area where they overlap. So can we name a point in the solution set for just the red? Well, we know that anything in this red section is a solution to the red equation. So I could plug this point into this equation and get something true. We also know that anything here is also a solution to the red equation because it is still in the red area. Okay, so anything in the red area is a solution to the red equation. The blue, on the other hand, right? This right here would be a point that is just a solution to the blue equation because it's only in the blue area. But this point over here that we just talked about is also in the blue area. Okay, so if we're looking for a point that is in the solution set for both, we are looking for a point in the area where the shading overlaps. Okay, so what we're doing here is we're setting up what's called a system of inequalities. Okay, similar to a system of equations where we are looking for points that are intersection points. Well, now we are basically looking for intersecting shaded areas. Okay, and why is that? It's because the two inequalities are working together as a system. So here we have another example right here. We have a blue equation, we have a red equation. Our solution set is anything in the double shaded area. So anything from here to here is a solution. We typically represent that by writing a S in our solution set, especially when it is not color-coded, like for a Regents question. So that's how we represent our answer. Now, I do have a question, something we haven't talked about yet. What about the points that fall exactly on the line? So I'm talking these points right here on this solid blue line and these points right here on the dashed red line, right? Well, we know that points on a solid line are solutions. So if I am here on this blue line, I am a solution to the blue inequality. If I'm on the blue line over here, I am also a solution to the blue line, but because I'm also in the red section, I am also a solution to the entire system. That's going to be very different from the red points, right? If I have a red point on the boundary line, that will be a solution to nothing, right? Because we're not including the or equal to's. So if I'm on this red line in the overlapped section, it's also not going to be a solution to my system of inequalities because it's not included in the red. So I have a question for you. Is the point 1, 1, the intersection point that's right here, a solution to the system of inequalities? Well, no, it's not. And the only reason that it's not is because the red line is dashed. Okay, so it's impossible for it to be a solution. But if you were unsure, we could check this. And we check this by plugging it into the inequalities. So 1 comma 1, x plus y has to be less than or equal to 2. Well, 2 is less than or equal to 2 because it is an or equal to. We should have expected that because it falls on the blue line. Now, when I plug it into the red equation, 4 times x, minus y has to be greater than 3. Well, that's 4 minus 1, 3 greater than 3. That is not a true statement because 3 is equal to 3, not greater than 3. Okay, so you have to be very careful with boundary lines. Dashed, not a solution. Solid, yes, a solution. So let's do some practice. Graph these systems of inequalities. So if we're graphing the system of inequality, we want to make sure we're graphing our boundary line, which means we have to start by solving for y equals. So 2x plus 3y greater than or equal to 6. I start moving things over, and I divide by 3. I did not divide by a negative number, so my symbol stays. And I get this as my boundary equation. Now I'm just going to keep this color-coded so we can see what goes with what. Y plus 3 is less than 2x. All we have to do is subtract 3. Okay, so we have our boundary equations. So now we're going to plot the points. So for this one, we have a y-intercept of plus 2, and we have a slope of down 2 over 3. Down 2 over 3, down 2 over 3, and in reverse, up 2 over 3, up 2 over 3. Okay. So now, will these points be connected with a solid or dashed line? Well, we have an or equal to, so that will be a solid line. So when I graph this, I can connect these with a solid line. Okay. Will it be shaded above or below? Well, it's a greater than, so that means we're going to shade above. So that's everything up here. And let me label this. Y is greater than 2. Okay. Now let's graph the second one. Y-intercept of negative 3. We have a slope of up 2 over 1, up 2 over 1. And we continue all the way through. And in reverse. Okay, now will these be connected with a solid or dashed line? Well, it is a strict inequality, so we would do this with a dashed line. Okay, so when I connect these points together, we want to make sure we have some spaces, but can also see the whole thing. Now, will it be above or below? Well, it is a less than, so it's going to be below. So we're going to be shading on this side. Okay. So now we can label our solution area with an S. So where do we shade? Where we shade where the overlapping areas are. So that would be in this area right here. So now, quick question. Is this a solution? Yes, it's a solution because it's in the solid line in the overlapping shaded area. Is the point of intersection a solution? No. Why not? Because the blue line is a dashed line.